Now we are going to focus on the topic of weeks 3 and 4, where the main concept is going to be sampling, and then once we understand sampling, we will go back to study the Fourier domain representation. So the first task for us is to look at the process of sampling. If you remember, we said that the first step is, so this is an introduction to the chapter on sampling. So this will be, for reference, Oppenheim and Schafer Chapter 4. Okay, please do keep that as the reference point. So we are going from continuous time to discrete time. We have a sampling period Ts, and if you remember, we had introduced the notation for the sampling, and said that we are looking at the expression x of n is obtained by taking the signal xc of t, c stands for continuous time, t equal to nts. Then in that case you will get x of n is equal to xc of nts. So this is the process of sampling. But now we are going to go in and take a closer look at the expression for sampling, and we start by looking at what is the Nyquist sampling theorem. We stated that previously, and we said that there is a theorem which says that as long as the signal is sampled at a sufficiently fast rate, sufficiently high rate, we can recover it. But let us, we are going to formalize it. So Nyquist sampling theorem, very simple theorem, very powerful theorem, has been the foundation based on which we can go from continuous time to discrete time. Okay. So the theorem states that let the continuous time signal xc of t be a band limited signal, and since all of you have studied discrete signals and systems, you know what a band limited signal is. I will anyway sketch it for you. Band limited signal with a continuous time Fourier transform xc of j omega, which is equal to 0 for all frequencies greater than or equal to omega n radians per second. Okay, so maybe easier thing to sketch it straight away. I have the frequency response plotted of this signal. So this is xc of j omega, the magnitude, and what we are saying is this magnitude response goes from minus omega n to omega n. It does not need to be symmetric, it can be, but we just draw it. So important thing is it is 0 outside of this band, from outside, greater than omega n and less than minus omega n. So this is a band limited signal. Band limited signal. This is the definition of a band limited signal. It occurs in many types of signal processing. It occurs in communication. So it's very, very important. So the Nyquist sampling theorem states that xc of t can be sampled and reconstructed without any loss of information if you satisfy this condition, that xc of t is uniquely determined by its samples, defined as x of n equal to xc of nts, where n equal to 0, plus minus 1, plus minus 2, dot dot dot, all the way to minus infinity to infinity, provided, this is the important condition, okay, the sampling frequency, okay, omega s, the sampling frequency is nothing but 2 pi divided by Ts. Okay, this is the 2 pi divided by the sampling period. this has to be greater than or equal to 2 times omega n. Okay, 2 times omega n. Okay, so what we are saying is, if I have a band limited signal which is band limited to the frequency omega n, then Nyquist theorem says that there is a rate, Nyquist rate. Okay, the Nyquist rate must be equal to 2 omega n. That is the minimum. Any frequency that you sample which is greater than Nyquist rate will help. We can represent the continuous time signal in the discrete time, and you can recover the continuous time signal without any loss of information. So, whenever there is a band limited signal and somebody asks you what is the Nyquist rate, sampling rate, you should take it as 2 times the highest frequency component that is present there. Now, the sampling frequency is 2 pi by Ts, 2 pi by the sampling period, and so basically omega s, the sampling frequency, is given in radians. 2 pi is in radians, T is in seconds, so you get radians per second. Okay, I hope you are comfortable with that, and this is what is happening here. It's a band limited signal, so let's go ahead and write it down. Band limited signal, this sampling period satisfies Nyquist theorem, satisfies Nyquist theorem. What does that mean? It says that the sampling period is greater than or equal to 2 times omega n. Okay, it's a band limited signal with bandwidth equal to omega n, right? Basically, that's the highest frequency component. This sampling period, the sampling frequency is greater than 2. So, this is 2 pi by Ts is greater than or equal to 2 times omega n, and therefore, Ts is chosen to satisfy this condition. Okay, as long as you have chosen to satisfy this condition, then you are guaranteed to be able to reconstruct a signal. So, this box which converts from continuous time to discrete time must be applied only to band limited signals, and it must also choose a sampling period that satisfies Nyquist. Now, the sampling period that satisfies Nyquist condition is not just a single value. Anything less than that is also okay, because see, if 10 milliseconds is a sampling period required for Nyquist sampling theorem, 9 milliseconds is okay, because you're sampling faster. Sampling period of 1 millisecond is even better. So, basically anything which is less than or equal to the Nyquist sampling period, that is good for us. So, basically this is what has happened. Now, this is where we have to derive a certain result which is very, very important for us. So, what is happening inside this block is something that we need to study carefully. So, let us take a look at what is happening. How do I go from continuous time to discrete time? Okay, basically how does this block work? So, I am going to draw it for you. I have a continuous time signal xc of t, it is a band limited signal, continuous time. I am going to multiply this one with another signal s of t, Now, s of t is an impulse train, and it is a train of Dirac impulses or Dirac delta functions, impulse train. Okay, and so this is summation n equal to minus infinity to infinity delta of t minus nts. Okay, please sketch s of t for me. S of t has got a Dirac delta, it is given by an arrow at time t equal to 0. Then there is another Dirac delta function at Ts, another one at 2 Ts, and so on. This is the sketch of S of t. What is the height of the arrow? we cannot specify because that arrow goes to infinity. So basically these are Dirac delta. So all you can say is you draw an arrow and then say that this is a Dirac delta function. Okay, and so what we have is a Dirac delta function. Okay, you have an impulse train, and S of t is an impulse train that will multiply. Now, we will look at the properties of the Dirac delta, but when you multiply one signal by an impulse train, remember that the signal, the S of t is 0 everywhere else except where the Dirac deltas are occurring. So the product will be non-zero only where the Dirac deltas are occurring. Everywhere else it will be wiped out. So you can see that in some sense this is like the process of sampling, but we just have to be careful. So this output, we call that as the S of t, xs of t, xc of t multiplied by the impulse train. So what you have is these Dirac deltas which are present. And what happens when they multiply? So if you have a continuous time signal like this and you multiply with the Dirac delta, you get the height of the function at that point, right? So basically these are now scaled Dirac deltas which are occurring. So these scaled Dirac deltas are passed into a very unique box which is going to convert these impulses to a discrete time sequence. So convert impulse train to a discrete time sequence. So in other words, it's going to look at that impulse height and then output a number which will then be equal to x of n. Okay, so at this point, input is all Dirac deltas. What is coming out is a sequence of real or complex numbers. So at this point, this is a sequence of numbers. How did you get these numbers? You looked at the height of the Dirac delta. And if the height was equal to 3, you put out x of n equal to 3. If the height of the Dirac delta was 2.4, you put out the sequence number as 2.4. So this is value, this x of n, the discrete time sequence, x of n is equal to xc of nts. Okay, so whatever was the value, or maybe we should write it as well, xc of nts is correct, yeah. So, but it's also equal to the places at those points, it's equal to x of s, but we will develop that. Okay, now maybe it's helpful for us to just very briefly review the properties of a Dirac delta, because we are using Dirac delta quite extensively. So properties of Dirac delta function. Dirac delta function. Okay, and the Dirac delta function is basically given by this time n equal to 0 delta of t. This is what it is in terms of the representation. So the definition of delta of t, okay, is given as a Dirac delta is equal to 0 everywhere where t is not equal to 0, and at where t equal to 0 it is undefined. Interesting function, right? Basically it's going to infinity, right? Unless you scale it, it will go to infinity. Now, how do we understand the behavior of a Dirac delta function? Typically it is done as a limiting process in calculus. So you think of a rectangular function which goes from minus delta to delta with a height of 1 over 2 delta. Okay, so basically the area of this rectangle, area equal to 1. Okay, and we call this as delta delta of t. Okay, now the Dirac delta can be visualized as what happens in the limit when these deltas tend to 0. So, as these deltas come closer, to keep the area constant, the height of the rectangle will keep increasing. Eventually, these two will collapse to a single point and the impulse will go to infinity. But this is a useful representation of delta delta of t. Okay, so this is a way for you to sort of visualize and keep track of what exactly the Dirac delta is doing, and therefore this is a important aspect. Okay, and now comes the two properties of the Dirac delta: minus infinity to infinity delta of tau d tau. That means, if I integrate from minus infinity to infinity and the delta occurring at the origin, this integral is equal to 1, the area under the rectangle. Now, it may be difficult for you to visualize with the Dirac delta, but you can look at it in terms of this rectangle and say, I know. Area of this rectangle is going to be equal to 1, and so whatever the value of the the triangle, you are going to see this area as value. Now, once you think of it as a Dirac as an impulse, then when you do minus infinity to infinity, you take a signal x of t and multiply it by this Dirac delta, delta of tau d tau. This will be equal to not 1 anymore, this is called the sampling property. Whatever was the value of the function x, that is what will show up. This will become x of 0. Okay, this is what scales the Dirac delta. So, very, very important that we keep this picture in mind. And so, when you multiply a continuous function by a Dirac delta, then what happens? You get a Dirac delta which has got a scale factor associated. It is not just going to infinity anymore, it has got a scale factor associated to it. And when you integrate from minus infinity to infinity, what comes out will be the scale value. So, that is why we are able to do an operation which looks like this: multiply by an impulse train. Okay. Now, so that you want you to sort of think of sampling as a very interesting and very exciting, insightful application of signal processing. So, I will give you an interpretation of sampling. Okay. Now, assume that there is a wheel with 8 spokes, okay, like your cycle wheel or any wheel that you have. Okay. And on the rim you make a mark, one red mark. Okay. Now, this wheel, let us say, rotates at 1 revolution per second. 1 revolution per second. Okay, very, very interesting. Now, if you take a camera and you click the shutter at the recommended, so basically camera shutter speed, and here will be the observation. Okay. Now, supposing the wheel is rotating at 1 revolution per second, that means in 1 second this red dot will come back to the starting point. Now, if my camera is 1 snap per second, then what does it say? It took a snap, it's at one position. After 1 second, it took another snap, so it says that the wheel is stationary. Is the wheel stationary? No. But the reason you think that it is stationary is because you were, looking at the rate of. On the other hand, if I took 4 snaps per second, okay, then what will you say? At snap number 1, okay, the dot is here. this is n equal to 1. Snap number 2, this is 2. Then snap number 3, it's here. Snap number 4, it is here. Snap number 5, it is here. Snap number 6, 7, 8 and so on. So you see the dot is moving. Okay, there is no ambiguity. You know that this thing is moving forward at a certain rate, and you can easily compute what the rate at which. So it is, the observation will be that it is rotating clockwise. Rotating clockwise. Okay, now here comes the most interesting part of it. Okay, supposing you take one snap every 0.9 seconds. That means just before 1 second. Okay, just before 1 second. So first time, where was the circle? It was here. Okay. Now the next time instant, it's at 0.9 seconds. So so this is at n equal to 1. Okay, where will the dot be at when you are going to take the second snapshot? It has not yet completed the circle, so it is somewhere close to the, so this is n equal to 2, then n equal to 3 will be even to the further left, n equal to 4 it will be here. What will be your conclusion? You will say that the wheel is rotating, but it is rotating counterclockwise. Counterclockwise. Okay. Now, I am sure you have watched in movies or in video clips, when a car is moving, at one point you see the wheel moving forward, and as the car is slowing down, you will see that it looks like the wheel is moving, rotating in the reverse direction. You've gotten used to it, but what is happening there? It is precisely sampling. If you satisfy Nyquist, you will know which way the signal is, the wheel is rotating. You must sample fast enough. If you don't sample fast enough, you will get erroneous conclusions. One could be that you may think it's stationary, or you may think that it is rotating in the counterclockwise direction. So you see, going from continuous time representation to a discrete time representation is very important, so that we have a sufficiently high sampling rate. If we do not have, then you get erroneous results. So this is a if Nyquist condition, if Nyquist theorem not satisfied, Nyquist theorem not satisfied, then we cannot recover the original signal. We cannot recover xc of t from x of n. Okay. Because this exact example, supposing I gave you samples n equal to 1, n equal to n equal to 3, n equal, you will tell me that the wheel is rotating counterclockwise, or you will say the wheel is not rotating. Only when you have sufficient high sampling rate, you will say it is rotating clockwise at the rate of 1 revolution per second. Okay. So this is the reason why understanding sampling is very important. We are all used to seeing this wheel rotating backwards. Actually, wheel is not rotating backwards. It is just that the camera that is capturing it, it is not clicking fast enough, and therefore the wheel looks like it is rotating in the wrong direction. Okay, so this is what sampling is. There is this Nyquist theorem which is extremely powerful, but it says that you must sample at a rate higher than 2 times the highest frequency. Only then you will get a discrete time representation which can be converted back to the continuous time and without any loss of information. How did we do it? We took these Dirac deltas and multiplied it with the continuous time signal and then converted it into a real number. Now, what does this do for us? What is happening in terms of the representation? What happens when I don't satisfy Nyquist theorem? All of these things come into a very rich theory which we will discuss in the next session. So we stop here. Please do read Oppenheim and Schafer Chapter 4, and we will pick it up from here and build on the theory of sampling, and that is the focus of the next session. Thank you.